Like, is there an algorithm you can follow on these? Not really. There's certain things. No, there isn't, because how many different ways are there to write a formula? A lot. You know, even in the confines of the math that you know, like we don't know. You know, you're relatively at the beginning of your math careers. I hope so. I hope you take a lot more math. I hope you do, because you know what happens after you get through calculus and maybe your first year of college math? Math goes off on all these interesting places that are very different than where you are right now. So I highly recommend taking more math. So what, like, when you looked at this, what did you notice first? What was one thing you noticed? What's one thing you've been taught to do, maybe? Nothing. You have never taken a math class before in your life. You've never been taught anything. Find the differences. You know, so you looked at it and you're like, okay, fine. I see 3, 5, 7, 9. So you got odds. Now, are we being told to come up with an explicit or a recursive? It did it? It just says a formula?
Yes.
That's nice, isn't it? Because sometimes one is much easier than the other. And sometimes one is easy and one of them is ridiculous. Like Fibonacci, straightforward as a recursive. Did anybody look up the Fibonacci explicit formula? Well, I'll look it up when you guys are working on something and put it on the board. It's pretty entertaining. So does anybody have, anybody have a hint? Should I use recursive or explicit? Yeah.
I got an explicit.
Yeah, what'd you say?
S of n equals to 2 to the n and then minus 1.
2 to the n minus 1?
Yeah.
Like this?
Yeah. Like this.
So this is 1 and this is 2 and this is 3? Are you sure it's not plus 1?
It's plus 1.
I think it's plus 1, yeah, there we go. 2 to the n plus 1? And what does it start with? N equal what? I think it's n equal.
Wait a second. I'm sorry.
No?
I'm sorry.
Go ahead.
I said the wrong one. Okay.
Oh, so yeah.
It should be 1 plus n to n squared.
1 plus what?
N squared.
Like this? Like that? Got it. Excellent. Is that a little better? Yeah, I mean, so you look at that and you look at differences and you see odds, but then you also might notice you subtract 1 and it's a square, it's a square, it's a square, it's a square, it's a square. You can look, I mean, there are many things to look for, but there's some pretty common things. I mean, you look for powers, you look for differences, you look at the prior 1 term or 2 terms. I mean, theoretically, the recursive form, like I could have like some super Fibonacci, which is like 1, 1, 1, 1, and be like, okay, then it's 3, and then it's, 1, 3, 5, right? And then what? 9, 17, right? Finding it explicit for that would probably be equally as challenging as the Fibonacci itself. So you're kind of limited in that it's just starting out, so they're probably not going to bludgeon you with something too complicated. Okay, any others? Can anybody tell me one thing that's kind of annoying about this notation? Cameron?
It's an S.
Well, in particular, S is bad, but what else is not so cool about it? Well, you have to use subscripts, right? But what's interesting about the notation is the subscripts are actually like bigger than the letter itself, you know? And also S is, I don't know, mathematicians are terrible sometimes at choosing letter representations. The idea is we need that 1, 2, 3, 4, 5, ... to end, because we need, the order matters. We need to have, it's called an index. So it has a limit L written. How do you say this out loud right here? Someone say this out loud. Can someone say that out loud to me?
The limit of n.
The limit as
N tends to infinity.
Of
S of n
equals L. And this is a phrase, the first time, I mean, you've seen it before, potentially. If Sn is as close to L as we please whenever n is sufficiently large. It's awkward. Mathematicians like to use as few words as possible. They like to summarize a whole lot. So unfortunately, in this case, it kind of comes out a little confusing. But the idea is something is a limit in kind of hand-waving verbalizations if you can get as close as you want to it. For example, if I go halfway to the wall and halfway to the wall and halfway to the wall, if Cameron says an inch and you say a millimeter, if you say a billion, picometer or whatever closest, can you always get that close? With this operation, if I get halfway to the wall and then I get halfway to the wall, can I get as close as I want to the wall? Yeah. Yes. So if you guys come up with any distance from the wall, can I always get closer than that to the wall? Mm-hmm. So the wall, because I can get arbitrarily close to it, is the limit of the operation going halfway and then going halfway and then going halfway. So like 1/2 to the 1/2 to the end, the limit as n goes to infinity. What's the limit? 0, because you get arbitrarily close to 0. Whatever distance you come up with, I can give you an n value that gets you that close, or closer, right? If a limit L exists, we say that the sequence converges to its limit L. If no limit exists, we say that the sequence diverges. We probably, it's always kind of creepy when it's real slow. So, does anybody know different ways in which sequences can diverge? -1 to like the n power, right? Yeah. So a sequence can just go back and forth, right? Does it get arbitrarily close to something? No, it never does. There's also sequences can just blow up and keep on like go to infinity, like 2 to the n. Does that approach anything? No, infinity is not a number. Infinity is what is infinity? It's a concept. It's a concept, and it's a really cool concept. You can preview of things that you can study later in undergraduate mathematics. How many rational numbers are there? What's a rational number? First 5 letters. What is it? Yeah.
Things that you can express in a fraction.
As a fraction of integers. Yes, exactly. Right. So any number that you can write as a fraction of integers is a rational number. Great. What's an irrational number? A number that you cannot, right? So like the square root of 2, right? How many rational numbers are there? There's an infinite number of them, right? How many irrational numbers are there? There's an infinite number. Did you know there's more irrational numbers than rational numbers? So you can have sets that are infinitely large, but one is bigger than the other. You've heard of this before. You've heard of like hotel infinity. Okay, you have a hotel. There's an infinite number of rooms. Okay, I'm working at the hotel. Brenda here shows up with a bus with an infinite number of people in it. They all come off the bus, and I say to the first person, go to the first room. I say to the second person, go to the second room. I say to the third person, go to the third room. I say to the nth person, go to the nth room. So an infinite number of people have come to my hotel, and do they all have rooms? Yes. Right. Okay. So my hotel is now full. Right. Like, great. Okay, that's nice. Another bus shows up with an infinite number of people, and I say, no problem. Why? Well, I get on the intercom system of my hotel, and I tell everybody, look at your room number. Go to the room that's twice. That's double your room number. So the person in room 1 goes to room 2. The person in room 2 goes to room 4. The person in room 3 goes to room 6, right? And then the new bus, I tell the first person to go to room 1. I tell the second person to go to room 3. The next person to go to room 5. So to be clear, an infinite number of people showed up and got rooms, and then an infinite number of people showed up and got rooms. Infinity is cool. Okay, you ready to learn more about this stuff? Some of these examples, I'll keep these on the board right here. What do you think about this first one, A? Do you think that one do you think it converges or diverges?
Converge.
Why? Less than 1. Nice. Exactly. Right. What about the next one? What about the next one? What about the next one? So you're pausing for a second because I'd imagine does B exactly match either one of these? Doesn't exactly match it. So we want to try to make it look like a piece of what is shown in the upper two. So what might we do to B? I don't like negative exponents, so I'm going to rewrite them. What am I going to write this as? I'm going to rewrite this as what? 1 plus what? Over. Oh, it's minus on top. Yeah, sorry, excuse me. It's minus. That is important. No, not really, but so does it converge or diverge? So as n goes to infinity, you can logic this out. Because of number 2, what do you know about this thing right here? That goes to 0. What does this go to? 0. So this whole thing goes to 1 over 1. So what does the whole thing go to? 1. This thing goes to 1 specifically because we know that this goes to 0 and this goes to 0. Oh, and hey, did we already talk about this one right over here? Yeah, what does this thing do? You can literally write out the term. So if n is 0, let's start with 0 here. If n is 0, what's our first term going to be? It's going to be 2, and then what's it going to be? 0, and then it's going to be, and then it's going to be, so this diverges. Correct. Nice. So this says a convergent sequence is bounded. Do bounded sequences always have to converge? No, we just saw one. 2, 0, 2, 0, 2, 0. That's bounded, right? Sine and cosine, right? Sine and cosine, they don't converge. They are bounded, but do they converge? No, they live inside a room, but they don't stop at any one thing. Monotone. Always up or down. Have you seen this phrase before? Ever seen monotone? Just means it's always going up or always going down. It's like what? No, were you saying something different?
Music.
We're using music. I was like, sometimes I get things wrong. Okay. So what we're going to do is we're going to talk about what happens when you start adding these terms together. Start adding these terms together. So what does it become if we start adding these terms together? A series. And you've looked at series before because what have you done in your last class? You've looked at what? Your last class, AP/AB, breaks down into two sections. Breaks down into two sections. The first half of the class covers what, and what's the second half cover? Yeah, okay. So when you were first studying that second thing, integration, how did you find the areas of things? Summations of really long series of numbers, sequences of numbers, right? So have you looked at series before? So you were at, there's that guy, his name begins with a letter R. Yeah, this goes to 0. It's 1 over n goes to infinity, so this thing does go to 0. Sure, the sequence does, right? What we're going to be looking at, which we're much more interested in, is does the series, meaning does the sum of the terms. That's what we're really going to be looking at for the next little while. So this is just a preview. We haven't talked about this one yet. This was just an example here that they give you right at the beginning of this section. Looking at that, it's 1 plus a half plus a third. Are the terms getting smaller? They are getting smaller, right? So do you think that the sum of the terms is going to converge?
No.
Or do you think it's going to diverge? But they're getting infinitely small. But they're getting infinitely small. What kind of series is that? Anybody know what kind of series that is? What? Someone said it. It's geometric. Why is it geometric? Times 0.1. Where? What? Can you give me a whole sentence?
S sub n is equal to n times
S sub n minus 1 times 0.1. Yeah. So what exists between any consecutive two terms? A what? A common ratio. Yeah. So in the terms we have seen so far, is there a common ratio? Yes, there absolutely is. There absolutely is. So what's fun about this is that can you use a calculator? I mean, you probably did this with your original Riemann sum analysis, and you would like add things up, and you'd like. Do you remember do you ever make tables, and you would look at what the tables sum to, and it would get to like 1.9, 1.999, 1.9999. You're like, oh, it goes to 2, right? That's generally, is that an exact method of proving the limit? Not exactly, right? That's looking at it and going, I really, really believe it's going to go to something, right? I really, really believe. So if I ask you to, let's look at this one right here. 0.004 plus 0.004 plus 0.0004, right? Oh, did I skip one? Sorry.
No, your second term says like
Oh, I just duplicated it? Nice. Good job, Mr. Seamon. So the real question is, can we... Man, did I mess it up again?
0.04.
This is where I'd like to pretend that I was doing it on purpose and being like, man, are they paying attention? No, that was just me totally messing up. So the real question is, we've looked at limits. We would love to be able to write this sum as a limit and then evaluate the limit to come up with the actual sum. You understand what I'm saying right there? Has anybody ever worked with the summation of geometric series before? It might be something you've seen in other places. 0.04? If we pulled out, so you want to do 0. You want to pull that out? Can we do that? Or do you want to point 0.04 out? You want to do 0.04? Okay, that's fine. If we pull out 0.04, what's left in there? 10 plus 1? Is that true? Did I do that right? You really did help me. My basic math skills are apparently going down the tubes. Is that correct? Seems right. Right? We can point. Yeah, nice. Okay. So what's the third one in the series going to be? It's going to be all three of these, right? Like this, right? If we wanted to write that all out, we'd write it as what? 0.004 times what? Plus 10 plus 1. It's kind of nice. So the idea is, could we write something more general now? Is it possible to write something more general now? What do you think? So the idea is, our goal would be, we're not going to do it right now, but our goal would be to try to do Sn and come up with a formula for the nth summation. Does that make sense? And there's many different ways to play around with this. I like this. I mean, I like this because we get 1 and 10. I mean, it's pretty easy to see what the next one's going to be. It's not point zero. Is it 0.004 or 0.04? Did I factor out the right thing there?
Yeah.
1, 2. I did? Yeah. Nice. So you can kind of build it up, but the point is, you need to. Even if we built an explicit term, doesn't necessarily mean we'll be able to properly write the formula for it. You have to be very careful about it. But there's lots of different ways to play around with factoring to come up with a sum. Does that kind of make sense? If you play around with it enough, you end up with this right here. I just put it here for fun. It's a good time. So what is that equal to? That right there is what you get. That's a really nice, clean, explicit formula for the sum of these terms. If you play around with it enough, you end up with that right there. It's kind of cool. It's pretty neat. Why is it really nice to have that? What can you do with that? What's the point of finding this explicit formula? Cameron? Yeah, that's the first thing. You could find it at any n value without knowing any of the prior ones. But then also, what could you find? You could find the sum of how many of them. You could do the limit, right, and see what happens. Let's look at this, and let's just look at it logically. If n goes to infinity on this, if n goes to infinity, what happens to this? This goes to 0, right? This is static, right? This is just 0.96. So this goes to 0, so 250 over what? So this, if you do the limit as n goes to infinity of qn, you end up with 250 over 0.96, like this. Is it like that? Nice. Pretty cool. So does it converge? Does the series converge? Yeah. If you can actually find a number, it does converge. Uh-oh.
It's A1, parentheses, 1 minus R to the n.
All over?
All over 1 minus R.
1 minus R, exactly, right. You can do this out by writing out the C, you can write it out in general terms. If S1 is A, and then you keep on going with that. So what would be S2, the sum of two terms? If A is your initial, if A1 is your initial term, what would be your next term? Constant ratio. You're summing one term plus another. So if the first term is A1, the next term is going to be A1 plus A1 times R. Exactly. A1 plus A1 times R. Does that kind of make sense, everybody? A little bit? Kind of? Maybe sort of? Yes? No? How many people have... Raise your hand if you have any memory of doing this whatsoever in your life. A little bit? Kind of? Maybe sort of? Okay. So, what happens... So, do geometric series always converge? What do you think? Do they always converge? Or what do you think? When do they converge? When do they not converge? So as you go to infinity, yeah. So if we take an infinite number of terms, when do we think the geometric series converges, and when does it diverge?
I think maybe the absolute limit of R is less than 1.
Ah. Yeah, let's look at this formula you came down here, right here. So this right here, what happens right here if R is too big? What happens? It blows up, right? It gets really, really, really big. So if R is greater than 1, exactly. So if R is just 1.1, what happens when you raise it to a power that's enormous? It becomes really, 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 really big. It becomes really, really, really big. Exactly. Right. Okay. So this is what you see in general terms. your first term, you're adding your second term, you're adding your third term, and so forth, like this. What's the only difference between the first and the second lines? The first one ends. No, literally, the first one ends. That's all. That's the only difference whatsoever. That is the only difference whatsoever. That is it. That is it. Now, summing an infinite geometric series is fun because we have a formula for it and we can take a limit, right? So let's say our initial value was 7 and our ratio was, what do we want our ratio to be? Let's make this converge. Someone pick a ratio that we know will result in a convergent geometric series.
1/5.
Like a half, right? So if this is your A value, if that's your A value and that's your R value, what limit can you set up? You know, the sum is going to be the limit as n goes to infinity of what?
7 times 1 minus 1 to the n. Or 1 minus 2.
Like this? So n goes to infinity, what happens to that top term?
7.
Becomes 7. A half. So what does this go to? Yeah. So is it relatively nice? Is it relatively nice? What happens if I change this to 3/4 or 5/6? No. 3/4. It would still converge, right? What's the only thing that changes? The denominator changes, right? So when you're dealing with a convergent infinite geometric series, what does the formula really kind of summarize down? There's something you can kind of eliminate a little bit.
A over 1 minus.
Yes. Do you remember this? This might strike something in your head. A over 1 minus R. Do you remember that?
Oh, it's like B.
Do you remember that? Yay? No? You're not sure? This right here, this section of the formula that you just gave me, this is always going to go to 1 when R is between negative, when R is between 0, is less, the absolute value is less than 1, right? Kind of makes sense? A little bit? Okay. But what about a finite geometric series, meaning it ends? What happens if I wanted, see look, we just figured out what this goes, when it goes to an infinite number of terms, it took us like 10 seconds and we got 14, right? But what happens if I said, what's the sum after 29 terms? What do you do? Oh, do you just put 29 in? Does it work?
Yeah.
Come on, have confidence here. That's the whole point of this exercise. The whole point of having an explicit formula is that nothing is really going to change. You have an explicit formula, so if you want to know what happens as if you have an infinite number of terms, you have to take a limit. But if you want a finite number of terms, all you do is plug in 29. Now, when you're evaluating, is it a little bit more annoying? Sure. If you have to write down the exact fraction representation of this, that's not super, it takes you a little bit longer. It's not like, oh, this goes to 1, so it's 7 over a half, so it's 14. But the whole goal of having an explicit formula, is that you can stop whenever you want to, or you can just keep going. Is that semi, we're doing okay with that? Ish? Yeah? Okay. So, example-wise, here we go. Let's do a couple of these together here. So let's do the first one. For each of the following infinite geometric series, find several partial sums and the sum if it exists, meaning the sum as you go on forever. So when they say find several partial sums, I mean maybe make a table and see if you can predict where it's going. Let's just go to the sum itself. The first one, what's our first term? What's the A value? 1. What's our R value? 1 over 2. So what's our sum going to be? So what's this going to go to? 2. I'm just dropping the one. No, I'm dropping the other one because we know it's going to go to 1. So yeah, what was being said was, yeah, you could do this times 1 minus 1/2 to the n, right? Like that, if you wanted to. So it's 2. Okay, that's nice. What about this one? Is that yeah. What is R in this case? R is 2. R is greater. The absolute value of R is greater than 1. So what do we know? Diverge, yeah. Do you know that 3 dots thing that I just did on the board? Therefore. Therefore. Yeah, good. What about this one? This is where it gets more fun. I like these. What's this one? Well, what do we think our A value is? 6. And what's our R value? Looks like it's negative 1/3, right? Negative 1/3. Are we allowed to have an R value that's negative? Yeah, sure. The math for setting up that formula doesn't change. So can we use the formula?
Yes.
Yeah, so we know the sum, what's that going to be? 6 times, like this? Yep. Yeah, well, I'm just going to write out the whole thing like this. Is that what you wanted right there? So do we think this works? It's going to be 6 over what? 4/3, yeah. So what's that going to be? 18 over what? So what's that going to be? Does that work? So is it okay if R is negative? That's my question. Yeah, it is. It is. It's kind of cool that it doesn't really matter. Okay, so geometric series is a way that it comes up in your life really, really frequently in the form of, this is the universal time for money. Money. The most human life. Money. Right. In what aspect of money is the geometric series appear? Money in banks. Right, exactly. Why do you put money into a bank? There's big reasons. There's many reasons. Interest rates. It's also keeping money safe, so you don't grab the money under your bed. Right. You know, like, so the idea is to put money into a bank and then it compounds. Right? It compounds. So the idea is you put a certain amount in and then there's a certain amount of interest that you earn at the end of the month, right? The thing is, banks don't operate on, you could say daily interest, you could say monthly interest, you could say yearly interest, right? Is that what banks do? Yeah, they continuous interest. Yeah, you got it right. Exactly, right. So do you ever do money compounding problems? You remember those from Algebra 2, maybe? Like if you put $10,000 into a bank account that's earning 12% yearly, how much money do you have at the end of 10 years? That is structurally identical to what we just did. It's structurally identical. Because what are you doing? Exactly. Right, exactly. So, I think here it is, right here. Sorry, right here. People who save money often do by putting a fixed amount of money aside. To be specific, suppose $1,000 is deposited every year into a savings account, earning 5% yearly. Compound 5% a year compounded annually. What is the balance BN in dollars in the savings account right after the nth deposit? So let's read that one more time. You're putting $1,000 into an account that's earning 5% a year, right? That's a lot. Well, no, I guess everything's relative. Can you actually shut the windows now because the construction's easy? If I put $1,000 in, and then I put another $1,000 in, and then I put another $1,000 in. It's not just 1,000 plus 1,000 plus 1,000 plus 1,000 plus 1,000. What are you earning every time you put money in over a certain amount of time? You're earning interest on that money. You're earning interest on that money, exactly. So you can write this out as a geometric sum, and then you can add it all together and find out how much money you have after the nth deposit. Does that kind of make sense? A little bit? Not really? So, does this kind of make sense the way I'm presenting this, kind of going backwards in time? So if you wanted to find n of these, if you wanted to add these all together, you would have to play around with pulling things out of each of these. Remember when we started this off, you could pull it like 0.04 and you would start noticing a pattern? You can go look at, I'm not going to go through line by line of like the algebraic manipulation, but if you go through this, you end up with Bn, the amount in there is 1,000 times 1.05 to the n minus 1 all over 1.05 minus 1. If you go through all this algebra right here, if you go through it all. And this is on page 474. You can look it up. 474. I am not, again, am I ever going to have you prove or do any of these things out like this? No, I'm not. The nice thing is, you now have an explicit formula. What happens as n goes to infinity? You should expect this. What happens as n goes to infinity on this one? Yeah, it goes to infinity, right? Because what happens to this amount right here as n goes to infinity? It should make sense because every year you're putting in $1,000, so it's arbitrarily wrong, right? So you would use this to find things like how much money is in your account after 50 years. You guys kind of with me so far? A little bit? Kinda? Maybe, sort of? Yes, go ahead. Nice. That's, oh, we got to go to the, where's your homework, Michael? No, this is what the 1 through 10, right? Wasn't there? Wait, hold.